Hello, everybody. Math 225. We're just recording the going over of solutions for the sake of Isabel Bennett. So I will share my screen and I will go and open up the solutions locally on my computer. And that means I need to go Dropbox and my documents, fall 2020, Math 225. Solutions. 2, homework number 5. Here they are. Alrighty. So, let me just, whoops. What's this? Didn't want that. Yeah, okay, so we're ready to go. This improper integral, I'm going to suggest the comparison test for improper integrals. Notice that if I just hacked off a 1, then I get x times the log of x squared, and that would be smaller, at least for all the x's that are bigger than 2, which is the range of that integration. So the reciprocals go the other way around. The integral that I'm concerned about that's hard to do is going to be less than the integral from 2 to infinity of 1 over x log of x squared dx. So let me just see what happens to it. And so I give it a try, and it turns out there's a u substitution that can work for me, letting u be equal to log of x. Du would be 1 over x dx. And I would end up with a 1 over u squared du problem. And so the antiderivative would be a minus 1 over u. So I'm looking at a minus 1 over log of x plus c for a general antiderivative. And so I'll just pick out the minus 1 over log x as the antiderivative that I use in the fundamental theorem of calculus. I'll evaluate that between 2 to n, and I'll let n go to infinity. And because log of n goes to infinity, ultimately the limit comes out to 1 over log of 2, which is finite. So our improper integral, being the area under a smaller curve, also has to be finite. And so our integral converges. So this is the key. You've got to get your function to be less than a function whose improper integral converges in order to pull this off. Comparison tests are tough. Next one, you plan to approximate the definite integral below using the trapezoid method with n trapezoids where n is bigger than 1. So I say that this approximation is always going to be an underestimate, but why? So I check on the concavity of the function e to the minus x squared. I need to check on the concavity over the region of integration minus a half to a half. All right, so I take the first derivative because I want to take the second derivative. For the second derivative, I need a bit of product rule, and I get that expression that I've highlighted there. I can pull out an e to the minus x squared. So I get the second derivative is e to the minus x squared times 4x squared minus 2. Now, e to the minus x squared is always a positive number. So whether or not the second derivative is positive really only depends on whether the 4x squared minus 2 is positive. And so there's a couple of different ways of thinking about it. One way is just with a graph. You could just make a graph for yourself of 4x squared minus 2. It's a parabola. It opens up because there's a positive coefficient for the x squared term. It does start at 0, it's negative 2, but it opens up, and so it becomes positive at 2 points. We just have to find out what those are. And so we set 4x squared minus 2 to 0 and solve for x, and we get x is plus or minus 1 over the square root of 2. So we get a negative y prime prime for the x's that are between minus 1 over root 2 and 1 over root 2. Now, thinking about 1 over root 2, that 1 over root 2 is less than, is 1 over root 2 is more than 1 over 2, because root 2 is less than 2. So 1 over root 2 is more than 1 over 2. Minus 1 over root 2 is a little bit more than, is a little bit less than minus 1 over 2. The region from minus a half to a half is narrower than the region from minus 1 over root 2 to 1 over root 2. If y double prime is negative all the way through the bigger region, it's negative through that smaller region as well. All right, so over the region we care about, from minus a half to a half, y double prime is negative. That means that the function y is concave down over that entire region. Yeah. Oh dear, crapola. That ruins the entire homework assignment. That ruins the whole assignment. Yeah. Oh boy. Well, it'd be easy to grade the thing. Because now it would become a really hard problem to work, wouldn't it? Because like, yeah, I'm not really sure, like, yeah, see, it's going to change to concave up after 1 over root 2. And so like there'll be overestimates coming from the rectangles that are past 1 over root 2 all the way up to 12. Now, they're kind of tiny rectangle. They're tiny trapezoids because the curve is getting so close to 0 after a while. So it actually is kind of going to be really hard to figure out, yeah, what that is. Yeah, so probably everybody's got full credit on the second problem. So let's pretend that there was a divide sign between the 1 and the 2. Then we would be concave down the whole way. And so all of our trapezoids, no matter how many or few we choose to have, they would have their tops lying underneath the curve. And so we would be in underestimate territory. So I'm looking over at Tristan, and I'm very suspicious. Tristan, I bet you knew that it should have been 1/2.
I really did.
You didn't?
I didn't even think about it.
This is hard, but hey, this is Calc 2. You know, who knows? Maybe he wants us to suffer. Yeah. Yeah. Ouch. Okay, so everybody's got full credit for that one. Okay, how about this number? How about the extra credit? Did anybody get a shot at the? Did anybody try the extra credit? Huh? Yeah. Yeah. Well, like when you look at it, this one, I'll just show you here. You can do it. So you do the y prime. It's -2, x is -3. You square that, and that's a +4, x to the -6. So 4 over x to the 6. And so your surface area is 2 times pi times the f of x times the square root of the stuff. So integral from 1 to infinity, 2 pi, 1 over x squared, square root of 1 plus 4 over x to the 6. So thank goodness, you only need to know if this is finite surface area or not. So what we got to do is some kind of comparison. So I look at this stuff, the x part of the integral, and I think, well, I could make one fraction by getting a common denominator inside that square root. And then I could think of doing the square root of x to the 6 plus 4 and the square root of x to the 6, which would be an x cubed. And I can stick that x cubed on the bottom next to the x squared to get an x to the 5th. So I'm now at this stage here that I've selected. Now, that looks a lot to me like basically square root of x to the 6th over x to the 5th. I just need to make sure that I get to be less than something that'll converge. So I go for a less than. I replace 4 with x to the 6th. Because once x gets big enough, x to the 6th would be bigger than 4. So this that I'm selecting now is less than this that I'm selecting now for big enough x's. And then this new stuff is twice x to the 6th, and I can easily take square roots and come up with 2 over x, root 2 over x squared. And so now I just got to wonder, what about the improper integral from 1 to infinity of 1 over x squared? And that's a p integral with p bigger than 1 that converges. So, you know, a root 2 times it would converge. And so we're fine. Our surface area will be finite by this comparison. So did anybody think they got the bonus? Inequalities are tough. Inequalities are harder than equalities. In math, an inequality is actually usually more valuable than an equality, even though it doesn't seem to deliver as much information. So I guess everybody's getting a 10 on this. Well, I don't know. Depends on how you handle the comparison in part 1. So sorry about that, and I will stop the recording here.